on. So heating at constant pressure. So, and I just said constant pressure for now, to make this a little more straightforward. But also, because if you think about it, when you're in the lab, and let's say you want to boil some water, you're heating it at constant pressure, right? This is what I'll say is ubiquitous. When we heat, we're almost always heating at constant pressure, okay? So let's put this together, okay? And let's start by reminding, I'll remind you that delta S, okay, from T initial to T final. So from initial to final, right? dq reversible over T initial, okay? Well, and I'm going to expand that now, and I'll say I know delta S, I can say is S T final minus S T initial, okay? And so now I'm going to start writing this as S T final equals S T initial. So I'm going to add the initial temperature over to the other side, plus integrating from initial to final conditions of dq reversible divided by T. So what do we do with that dq reversible? Well, I will remind you that heat at constant pressure equals delta H, okay? And we also know, if I can keep going with this, I know that that also equals Cp times delta T, okay? Or, in other words, dH equals Cp dt. So just remember, heat delivered at constant pressure is called enthalpy, which is also the constant pressure heat capacity times dt, okay? So I'm going to rewrite this expression now as ST final equals ST initial plus, and then now, so I wrote TI, TF, that's technically not correct, right? It should be QI, QF, so I'll just write IF here. But now I can replace this whole expression with Cp dt divided by T integrated from Ti to Tf, okay? And now I haven't specified what my initial temperature and my Ti or Tf is, but if you look at this graph here, okay, so on this scale here, we've got Cp divided by T, or S, all right? And if you notice what happens when we start heating, we heat a solid. When it gets to that melting point, just as we described, right, like in this picture right here, there's a jump. That's the latent heat of that phase transition, okay? So what happens over that range? Can we use this whole equation? Well, as it turns out, no, we can't. We have to start expanding it, okay? And I'm going to expand it via the following. Now I'm going to say Sm, and I'm just going to start writing T, and I'm saying Sm to deal with molar entropy, equals Sm 0, okay? And then now I'm going to integrate this from 0 all the way to T. And here's how this is going to go, okay? When I start at 0 and I start integrating it all the way through, I'm going to first hit the freezing point. I have to stop right there. I can only integrate this first integral from 0 Kelvin to the freezing point. And the reason for that is because we know the heat capacity of the solid is going to be different than the heat capacity of the liquid, which will be different than the heat capacity of the gas. So in other words, now on this integral, I can write Cp, constant pressure, molar heat capacity of the solid, okay, divided by temperature times dt. And we know that that CPM as a function, that this equation, CPM, okay, I'll remind you, I'll just write it up here. CPM is a function of temperature, right? Function of T. So you know from your working on your exam that we can supply a constant value into CPM, but a better approach would be to put an equation in there that is a function of temperature that will get integrated with respect to temperature, okay? So now that's the heat capacity of the solid, dT, okay? So now what happens as we keep increasing the temperature? Well, we have to pay the tax man for the phase transition. And that phase transition is melting. So that's going to be now plus delta H melt divided by T melt. Okay? And the reason why it's delta H divided by T is because, look, we're saying entropy equals all this stuff. We know that entropy is delta H divided by T. Okay? So now when I do this whole expression right here, the way this is written, this is only going to take me up to here and then to right here, right? The integral took me up to this point, and then by just saying plus this latent heat, that takes me up to this stair step, okay? Well, now I've got another phase to integrate over. And so now I can say plus, now I'm gonna integrate this. I'm gonna use melt. I wrote F right here, but just so we're not confusing that with like final and initial, right? The F was supposed to be for fusion. I'm gonna write melt, T melt, like for the melting point, okay? Now we can integrate this from T melting point to T boiling point, right? So this goes now from TF to TB, or the melting temperature to the boiling temperature. And we know that now that's going to be Cp, molar heat capacity of the liquid divided by temperature, D temperature. Okay? Plus, we know that there's now going to be, as soon as I get to that boiling point, the integral gets me that far, but now I've got some latent heat that I have to deal with. Okay? So that's going to be plus delta H of vaporization, or I'll say delta H boil, divided by T boil. Okay? But that still doesn't take me up to this generic T, whatever that T might be. Suppose it's like somewhere right here, right? Somewhere, some gas phase temperature. Okay? So now what I need to do is integrate over the phase of the gas. And so now I can integrate this thing from T boil to just T, whatever my T might be, right? And now that's going to be the molar heat capacity of the gas phase divided by temperature, D temperature. And let's box all of that up, because this, little did you know, turned into a mess in a hurry. Okay, so let's back up and talk about this. If I want to calculate the entropy, so notice that this is no longer delta S. This is just S. So this is like saying, what is the molar entropy at a specified temperature? Okay. Well, it's going to equal the molar entropy at 0 Kelvin plus the integral from 0 Kelvin to the melting temperature of the solid phase, which now entropy, I know I put a whole bunch of different equations on here. Entropy is dQ divided by T, which is the same thing as saying that it's delta H divided by T, which is the same thing as saying that it's Cp over T dt. So Cp divided by T times dt integral gives you entropy. Okay, so now we've integrated over the solid phase. But once we pass that melting point, we have to pay the tax man. We have to add that latent heat, plus delta H melt divided by temperature. Okay, so now we get past the melting point. Now we're in a liquid. Now we can integrate from the melting point to the boiling point. Okay, and that, you know, would be the heat capacity of the liquid, Cp over T dt, okay, plus delta H boil divided by T boil, So, right, if we go past the boiling point, we have to pay the latent heat of evaporation. And then now finally, if our temperature is, let's say, somewhere past the boiling point, then we integrate from T-boil all the way to whatever that temperature is. Okay? Not a good idea to use constant values of heat capacity in these integrals because this is a really wide range of temperature. And over a wide range of temperature, heat capacity will vary. So we have to supply like an equation, a function of T, and integrate that function with respect to dt. But don't forget, this is a function of T, but then it also gets divided by T. Okay? So I just want to briefly show then, well, how do we calculate delta H, just as a quick comparison. Okay? So as a quick comparison, I can calculate my molar entropy by the following. I'll say it's some integral, and I'm just going to say from 0 to T of Cp over T dt. And so that it also includes the delta H of that situation divided by the temperature at which that happens. Okay? And then plus we know if there's phase transitions, right, there's more and more of these. Okay? Well, let's back up for a second. How do we just calculate the molar entropy? How do we get that? Well, we can actually follow this same procedure. 0 to T. But now how is it different? Well, remember, delta H equals Cp delta T. So now in this integral, instead of saying Cp divided by T dt, it's just Cp dt. And now instead of saying plus delta H divided by T, it's just plus delta H of that phase transition. Okay? So these are two really important equations that we're going to explore in more detail in the computer lab activity, like how we can actually calculate what the molar entropy at a certain value is. Okay? What is next? Yes, okay. And so again, I'll note that, right, HMT minus HM0 would give us delta H, and specifically if T was equal to 298, then that gives us the standard change in enthalpy. Or similarly, when we look at this, okay, and T is 298, we can call this delta S standard. I'll put M for the molarity, okay, standard.